In one of the questions on Quiz 0, I asked you about drawing Lewis dot structures. In fact, it's kind of split into two tiers. First, just draw the structure, and in the next question, I ask you about molecular structure, VSEPR, and so forth. Those two topics are tied together, but I'm going to split it up just to kind of, again, keep going back over the basics. But yes, you definitely need to be comfortable drawing Lewis dot structures. And what I mean by comfortable is you look at one of these molecules and you go, oh yeah, that's easy. I don't even need a periodic table. You'll have a periodic table, of course, but you'll find as you draw more structures, as you get more practice, you'll know the number of electrons that each of these atoms possesses just out of habit, just kind of like knowing the alphabet and so forth. Now again, before I start going through some of these, why? We're going to be focusing a lot of our time on the D block elements. So why is it so critical to know Lewis dot structures? Because the D block elements don't use Lewis dot structures. What we're going to find is many small molecules, water, ammonia, carbon monoxide, will coordinate to a transition metal. So having an understanding of that molecule is very important because it will literally bind to a metal center. And you put yourself at a huge disadvantage of not understanding the molecule that's on the metal. Then how can you understand the complex itself, right? So again, this is where we're going to see what you've learned in general chemistry is really the tip of the iceberg as far as the nature of chemical bonding. But again, don't skimp on going back and relearning or refreshing your memory on these fundamentals. So our first molecule, hydronium, H3+1. So by convention, hydrogen is typically put first in a small molecule like this. Oxygen must be the central atom. Hydrogen cannot be the central atom in a molecule like this. And I put an asterisk there because guess what? There are examples of molecules where hydrogen is the central atom. But ignore that I just said that. So we have oxygen, and it's going to be surrounded by the hydrogens. But before I can do any of that, I need to do the electron count. And again, this is something that it's so easy to forget the fundamentals. So off to the side, we have oxygen. Oxygen has 6 valence electrons. Do you remember what valence electrons means? If the answer is no, that means you're in trouble. But fortunately, class is not started, so I can't legitimately yell at you. However, valence electrons are the S and P electrons, the outer electrons for a given element. And when we talk valence electrons, we're talking about groups 1 and 2, the S block, and 13 through 18, the P block. So oxygen is going to have 6 valence electrons. Hydrogen, well, we have 3 of them. And so that's going to be 1 electron times 3. So we're going to have 3 electrons. Again, it's really easy to forget the fundamentals. Hydronium has a +1 charge, right? So we have to deal with that charge. If you have a positive charge, that means you have lost an electron. Now again, that is something that sounds backwards, because you have to remember electrons have a negative charge. So losing an electron will actually increase my charge. All right, so we're going to start, I'll do it this way. So we're going to have 9 electrons here, but then our charge is actually going to cause us to remove an electron. So we have 8. Okay? So again, if you didn't follow that, pause the video, record, go backwards. because again, those little things are so easy. So many times I have seen a Lewis dot structure where this is interpreted backwards. So instead of a 9 electron species going to 8, you go from 9 to 10, and then it doesn't work, right? So again, that's usually a huge red flag if you have too many electrons or too few electrons in a charged species, that you reversed what you were supposed to do. Okay, so now 8 electrons. How are we going to do that? Well, the first thing is we put the atoms that are going to be connected to it, right? So we have 3 hydrogens. They must have a single chemical bond. The single chemical bond is 2 electrons, and it's represented by a line. So we have 2, 4, 6. Okay? So we've used 6 electrons, and we have 2 left over. Again, keep that running total going, because it's really easy, like I said, to get a little lazy, not do the bookkeeping, not do the electron count, and then get it wrong because you missed an electron or you added too many or whatever. We've got 2 electrons left over. Well, the oxygen, 2, 4, 6, as we count this up, 6 is not 8. 6 doesn't give me an octet. So what do we need? We need those 2 electrons. Now the oxygen has an octet. It is bound to or sharing a total of 8 electrons within the molecule. Something I didn't ask specifically on this problem about formal charge, and I'll get to that a little bit later on. But this is the correct Lewis dot structure for hydronium. Hydrogen does not have to, or does not obey the octet rule because it only has the s orbital. It doesn't have px, py, pz. It can't have an octet. So again, this is where remembering those rules. And something I see, a small molecule like this usually doesn't happen, but something I often see for a more complex Lewis dot structure is the student will just start putting electrons in wherever they think they need them. But the problem you run into is if you don't do the electron count, if you have, in this case, if you have 8 electrons, your molecule can only have 8 electrons, period. And what will happen is, maybe there's a more complex molecule and it should have 32 electrons. Well, they'll end up putting 40 electrons into the molecule because they think that will make the bonding better. But you can't do that because you don't have 40 electrons, you only have 32. So again, take the time to be very systematic of writing out the electron count, drawing your structure, and making sure it's consistent, right? Again, 2, 4, 6, 8. I've used my 8 electrons, octet rule is satisfied, everything's great. What I was about to say is, this is a correct Lewis dot structure, but it doesn't represent the 3-dimensional structure of the molecule. That gets us into VSEPR, valence shell electron pair repulsion theory. We're going to open that can of worms soon enough. Okay, so we're going to go from flat to 3 dimensions. But if you get the Lewis dot structure wrong, you're already the game's over. All right, so you got to get the Lewis dot structure right, and then you go forward. All right, so this is the kind of thing that if you've never seen it before, it can be a big hurdle. But I know you have seen it before because you're going to be taking a 200 level course. So this is why I'm not going to let any of you slide on this, because I know you have seen this. And I know you can do it. So take the time, work through these structures. I'm going to go through, not all of the ones from Quiz 0, but I'm going to go through a few others. So I'll pause the video, clean up the board, and go from there. But I highly recommend, as you're watching this video series, work through Quiz 0 first, and then watch the video. Especially, like I said, if you get stuck, or if you have a problem and you go, that answer I just gave doesn't seem to be right. You know, because usually you can figure that out of, okay, I don't know what the right answer is, but I know this ain't it. So that's why you want to use this video. If you simply watch me work through all of these and never do it yourself, I guarantee you that will not help you. And we're going to go from Quiz 0 to quiz 1 very quickly. All right, so you have been warned. For our next Lewis dot structure, we have carbon monoxide. Now in this case, when you only have 2 atoms, there's no central atom, so it doesn't matter the orientation that we draw it. Carbon has 4 valence electrons. Oxygen has 6. So we have 10 electrons to work with. Now, there are lots of different strategies you can use. What I like to do is first make a chemical bond. So that's 2 electrons. Because they have to have a single bond between them, otherwise they wouldn't be chemically bound. Then we start putting in the lone pairs. Even though you might suspect, hey, what about multiple bonding? We'll get there. So we have 8 electrons to work with. So 2, 4, 6, 8. I just distributed them on both atoms evenly. So we're done. Well, not exactly. We've used up all our electrons. 2, 4, 6, 8, 10. But now we have to see, do we obey the octet rule? 2, 4, 6. 2, 4, 6. Well, 6 is not 8. Obviously, we've got a problem. The solution is now multiple bonding, because if I just do this, if I do that, well, 2, 4, 6, 8, so the oxygen obeys the octet rule, but obviously 2, 4, that's not working. So now what I'm going to do, it doesn't matter which electrons I take. I take a set of electrons, 2 electrons, and I make it into a double bond. 2, 4, 6, 8, the oxygen's obeying the octet rule. 2, 4, 6, that's not working. So we take this, and now we have a triple bond. Now I'm gonna redraw to make this look a little bit better. And the reason why is we know from Vesper theory that the lone pairs repel each other. But if I did leave them up here, it wouldn't make any difference. So 2, 4, 6, 8, 10. So I haven't changed the number of electrons, but I have converted from lone pairs to bond pairs for 2 sets. 2, 4, 6, 8, right? So carbon has the octet, 2, 4, 6, 8. So does oxygen. So from a Lewis dot structure point of view, we have satisfied the octet rule, and this is the best structure. This is our correct structure. Later, we'll start looking at formal charge, and we'll see there's actually charge distribution within this compound. But for right now, this is fine. And again, we have a triple bond. So I didn't say that explicitly. So single bond, double bond, triple bond. And we'll see that you can't have a quadruple bond for the main group elements because you run out of orbitals. D compounds are a different story. The next molecule, carbon dioxide, CO2. By convention, the carbon, the first atom, is the central atom. If you have a molecule that is more complex in its formula, the central atom will be pointed out, or it might be a molecule that has more than one central atom. In other words, a molecule like ethane has 2 carbons, and each carbon has 3 hydrogens, and there's a bond between the 2 carbons. So technically, there is no central atom. Both carbons would be considered central in the Lewis dot sense. So we can put the carbon here, oxygen on either side, again for symmetry. So now again, we've got our formula, we've got the beginning of our structure, but we need the electrons. So carbon has 4 valence electrons. Oxygen, well, it's going to be 2 times 6, because obviously we have 2 oxygens. So now we've got a total of 16 electrons to work with. Again, the way I like to approach it is you know all of the atoms have to be connected. So they're going to require single bonds. 2, 4 electrons. So they're bound together. Now, there are two ways you could do this. You could start putting in multiple bonds if you think it's going to need multiple bonds, or lone pairs. I prefer first put lone pairs, then worry about multiple bonding. And the reason I say that is from experience, if you put a double bond in here or a triple bond and it's not supposed to be there, there's this inertia of erasing it. In other words, once you committed a double bond or a triple bond, you'll change everything else, but you won't come back and erase those bonds. That's been my experience of grading lots of student papers. So don't put multiple bonds in until the very end, even if you kind of know you're going to need them, which in this case we definitely are. 12 electrons, 2, 4, 6, 8, 10, 12. So I've put in all the valence electrons. 2, 4, 6, 8. 2, 4, 6, 8. The oxygens are happy, but obviously the carbon, that's a problem. We've only got 2, 4. We don't have an octet. By the way, this is something where, again, I see this happen all the time. Let's say I didn't do this part. Let's say I left off the bookkeeping. Then the next logical thing would be, well, I'll just put a double bond here and here, or I'll put in 2 lone pairs, and then I'm great. But you can't do that. You start with 16 electrons. That's how many you're going to have. And if you don't, well, then you're wrong. I mean, there's just no way around that. So what do we need? Well, multiple bonds. If I take that lone pair and turn it into a double bond, 2, 4, 6, 8, the oxygen is still happy, but 2, 4, 6. Well, my carbon is getting better, but still 6 is not 8. So we take this lone pair, 2, 4, 6, 8, 2, 4, 6, 8. Now we obey the octet rule, so everything is good. The relative position that you draw the lone pairs doesn't matter. In other words, if I would have taken this lone pair and left that one, it's still correct. It's only when we get to Vesper that we really have to worry about three-dimensional structure. So carbon dioxide has a carbon in the center and then a double bond to oxygen and then a double bond to the other oxygen, and that is the correct structure. Again, as we get further on and we start looking at the nature of bonding, I didn't mention this in the previous example, we're going to see, well, I have a single bond and then a double bond. Well, how do I get the double bond? The terms sigma and pi hopefully sound somewhat familiar, but we'll get to that a little bit later on. For our next structure, xenon difluoride, a noble gas compound. This is something you might have seen in general chemistry, and something we'll talk about in inorganic chemistry, that some of the noble gases actually do possess chemistry, which kind of goes against their name. It's usually the heavier ones, but xenon difluoride. Now, if we do our electron count, xenon is going to have 8 valence electrons. Fluorine, well, we have 2 of them, so that's 2 times 7. So that's 14 electrons. So we have a total of 22 electrons. Now, in this case, we've got 3 atoms. The xenon is going to be our central atom. Again, by convention, the first atom listed is the central atom, unless it's otherwise noted. So it has xenon with 2 fluorines. Well, 22 electrons, it's a lot of electrons. We'll see the bonding that's going to occur here. Regardless of the fact that it's a noble gas, we still treat it the same as we would any other compound. So we put in single bonds from the xenon to the fluorines. So that's 2, 4 electrons. So now we're down to 18 electrons. And again, do the bookkeeping. Keep track of your electrons, because if you don't, it's very easy to, again, make a mistake. What I like to do in this kind of a situation is, well, let's give everybody an octet starting with the terminal atoms. I don't think I mentioned that, but and again, it's just my preference. What you find for halogens that are terminal, so 2, 4, 6, that their chemical bonding is pretty straightforward. They have a single bond and then they have 3 lone pairs. So we just use 2, 4, 6, 8, 10, 12 electrons. Now we have 6 electrons left over. You might think, well, okay, like in the previous example, we start making double bonds. But there's a little problem with that, actually a huge problem with that. Putting a double bond in here, or a triple bond, is not allowed. Fluorine cannot violate the octet rule in the sense of having extra electrons, having more than 8 electrons. There are also some electronegativity issues we could talk about, but fundamentally, putting a double bond here or triple bond is not going to work. So what do? Well, we've got 6 electrons. Let's just put them on the xenon. So 2, 4, 6. Okay. So we've used up our 6 electrons. Now let's look at our octet rule for fluorine. 2, 4, 6, 8. 2, 4, 6, 8. So the fluorine is fine. How about xenon? So we have 2, 4, 6, 8, 10. 10 is not 8. But that's what we're going to have to go with. And the reason why is in the nature of how these type of molecules form and the orbitals that are available, we're not limited by the octet rule. So as we get to heavier elements, we're going to find, even if they're main group elements, xenon is still in the main group, that the octet rule sometimes just doesn't work. Again, hopefully the terms orbital hybridization are starting to ring a bell. I'll talk about that in a later series. But this would be the correct structure, Lewis dot structure. Again, with a molecule like this, there's a lot to unpack as far as its three-dimensional structure, the Vesper structure, and what's going on there. But this is the correct Lewis dot structure. Single bond to fluorines, 3 lone pairs on the xenon, and all the electrons are in, but we have an octet rule violation, and that's fine. The next molecule, nitrogen monoxide, that we're going to look at, seems pretty straightforward. 2 atoms. Nitrogen has 5 valence electrons. Oxygen has 6. So we have 11 electrons to work with. Now, what should be a red flag is when you have an odd number for a molecule. And in this case, the odd number is correct. Sometimes you'll get an odd number just because you counted incorrectly, but in this case, we're going to see their consequences. Okay, so first thing, single bond. So we have to connect the atoms. So that's 2 electrons. We have 9 left. So now I'm going to put them in as lone pairs. All right, so let's try and do it relatively evenly. So 2, 4, 6, 8. And now, what do we do with the last lone pair? Does it go on nitrogen? Does it go on oxygen? So let's put it on oxygen. 2, 4, 6, 8, 10, 11. Lost count there. So we've used all our electrons. So now First thing to ask is, ignoring this for right now, does this molecule obey the octet rule the way I've drawn it? And the answer is no. 2, 4, 6, 2, 4, 2, 4, 6, 7, not quite. So I'm going to put a double bond in. So I will take this. Okay. 2, 4, 6, 8. So nitrogen obeys the octet rule. 2, 4, 6, 7. Well, obviously, oxygen does not obey the octet rule, but for now, let's pretend that this one electron behaves the same way as a lone pair in the sense of satisfying the rule, even though it's not 8. And we can't really do anything besides maybe try and put a triple bond in here, right? You might be saying, because I'm sure you were screaming at the camera, well, don't stop now. Well, the fundamental problem with that is we'll have an octet rule violation if we do that. If I take this lone pair, bring it over here, then the nitrogen will have 10 electrons. It'll have 5 bonding pairs, which is not allowed. And if I take this over here, then I have essentially the same thing, just with the odd electron. So I can't go to a triple bond. Okay? You can try that, and hopefully you can convince yourself that that doesn't work. So we're kind of stuck with this, but there is one variable that we need to discuss. I've put the unpaired electron on the oxygen. Why not do this instead? So I'm going to have this structure instead. I haven't cheated. 2, 4, 6, 8, 10, 11 electrons. So we started with 11. We still have 11. We have our double bond. But I've moved the unpaired electron from the oxygen to nitrogen. Now, one of the things you may or may not have heard this term before, when you have an unpaired electron like this, we use the term paramagnetic. Another term, especially in organic chemistry that they use, is they call this a radical species or a free radical. What that's referring to is radical as in like aggressive, attacking things. Radical species are very chemically reactive. Doesn't matter what terminology you use. Well, it's got to be one or the other, right? Now, I say that with a huge asterisk behind here. Now, before I explain which is the correct structure, let me point out one very, very fundamental thing. When I'm looking at a Lewis dot structure, and the Lewis dot structure is not making sense, if I have some kind of weird octet rule violation that nothing I do can fix it, what that's actually telling me is Lewis dot structures are a lower level of how we interpret chemical bonding. Early in Chemistry 216, we're going to introduce a concept called molecular orbital theory. And in that case, we're going to analyze molecules like nitrogen monoxide in a very different, more rigorous way from the point of view of the electron behaving like a wave. So the correct Lewis dot structure that we're going to talk about here is still wrong in the sense of it's representing something that doesn't fit Lewis dot structure rules, but it's as close as we can get. So essentially, we're going to have to develop new chemical bonding theories to explain molecules that don't work with Lewis dot structures. Okay? So I want you to get that concept in your head because it'll make the transition much easier. Lewis dot structures usually work until they don't. And if they don't work, it doesn't mean that the molecule has a problem or that you have a problem. It means that Lewis dot structure, the theory, is incomplete. And again, this is going to be the first week of Chemistry 216. So how do we make the determination of which is best? This is where we have to bring in the concept of formal charge, where we calculate, all right, so for formal charge, we calculate the difference between the number of valence electrons that a molecule possesses in the structure versus the number of valence electrons that it brought to the structure. So nitrogen starts with 5 valence electrons. In this structure, it has 2, 4, 5, 6. We count 1 electron from each chemical bond. Remember, this line represents 2 electrons that are being shared between the nitrogen and oxygen. So 2, 4, 5, 6. There is a formal way to do this where you say 1/2 of 2, but the whole point of Lewis dot structures is to make it easy, that you don't have to do that. So what we say is the nitrogen has a -1 formal charge. All right. What about oxygen? Some different colors. Oxygen starts with 6 valence electrons. We have 2, 3, 4, 5. So it has a +1 formal charge. Now this is self-consistent because -1, +1, the sum is 0. Okay? It's a neutral molecule, so that's what we would expect. However, that's just one possibility. So let me just draw some divider. So what about if we have the radical on the nitrogen instead? How is this going to affect our formal charges? Again, nitrogen starts with 5 valence electrons. 2, 3, 4, 5. So the formal charge is 0. And for oxygen, again, we start with 6. 2, 4, 5, 6. 0. Which again is consistent because the molecule is neutral. Now, I'm going to say that this is the better structure, but why? Okay? It comes down to energy. If I have a positive and a negative, that's a potential. I'm holding these two back from each other because they attract, right? So what we find is the lowest energy for a molecule is to have the minimum charge, positive or negative, for that molecule, for the formal charges. Obviously 0 is as low as it's going to get. So in this case, the nitrogen has 0 formal charge, the oxygen has 0 formal charge, therefore this is the lowest energy structure, and therefore we assign the radical onto the nitrogen. Okay? Whereas here, charge separation is bad. Some molecules mandate having non-zero formal charges. That's their low energy state. So there's no trick you can do in some cases to get rid of that. If you're following along in quiz 0, the next question opens up that can of worms as far as I ask about Vesper and I also ask about non-zero formal charges. Okay, so all of these things are tied together. But as I mentioned, what we're going to also find is that you can't have a chemical theory or any theory like the octet rule where you say octet, 8, and then you have something like this where, well, you know what, it's still not obeying the octet rule, right? I kind of glossed over that, right? So we have 2, 4, 6, 7. 7's not 8, but that's the correct structure. Again, this is where we're going to have to switch gears and move to molecular orbital theory, and you can start reading ahead in the first chapter of your textbook on this. By the way, the OpenStax textbook also addresses molecular orbital theory in Chapter 8. So you might want to glance at that first before diving into your textbook. But either way, we're going to hit that, that theory very early in week 1.